The first team in session 2 is Team 9 Mooove.
Hello everyone, we're Team Mooove. I'm Ada.
I'm Carrie. I'm Caitlin.
I'm Batman.
I'm Julianne.
Yeah. Our product is a health and behavior monitoring system for cows. So it'll monitor like the health, activity, the environmental, as well as the location profiles of the cow. Our customer is officially Professor Babakia, but our target users are cow owners. So we went out and we sent out surveys, we visited farms just to get their feedback and find out what is actually important to them. Why is our product important? In the U.S., cattle production is one of the most important industries, but if we are able to reduce the risk of losing any cows to any diseases or illnesses, it will save them a lot of money. It also increases milk production and breeding if we keep the cows happy and healthy, and that also increases profits in businesses. And there are a lot of farms with more than 50 cows in a herd. I think there's like at least 100K just in the US. And with all those cows, it's really hard to keep track of everything, and that's where our product kind of comes in.
So where our project is right now, we've got the final shape of the anklet device that we're going to be attaching to cows, and we've got all the sensors working. All the firmware that's going on the end device is working, as well as the software responsible for passing the data, analyzing, and showing it to the user. We've still got to put in a little bit of work on the hardware, as well as the power management system, and the network topology isn't fully operational as we expected because of a failure on Kinetis's part. So the technical overview consists of a number of anklet devices that collect data about the cow through the sensors. They pass the data to the K20Z microprocessor pulls it from the sensors, passes it along the network. We originally wanted to do a mesh network, but as mentioned before, we weren't able to do that. So we have a star network. It passes it to the central coordinator node, which passes it to the router, which is a Minoward Max. That data is then sent to the cloud, where it's stored on AWS, processed and presented to the end user in the form of a website using the Django web framework.
So I was in charge of the wireless network over the farm. So the Anklet device that collected data, sensor data on Anklet devices, will send over the taken data to the central router wirelessly. And I was also in charge of the web services. So we have real-time dynamic web application hosted on Amazon Web Services, Elastic Beanstalk, and S3. We used Django website framework to process the data query, and we have actually, at the end, user-friendly data display using multiple JavaScript frameworks.
So I was in charge of the localization system, and originally we were going to use GPS, but then we realized that adding a GPS module to every single cow would increase the cost of the anklets as well as the power consumption significantly. So we decided to explore an alternative, which is based on RSSI values, which stands for Received Signal Strength Indicators, which is a value that can be collected within the Zigbee network. So how this system works is that several location beacon devices can collect RSSI data from the anklets, and then these values can be converted to distance estimates. And then when you have at least 3 distance estimates for one anklet, trilateration can be performed to get the location. I was also in charge of the social profile data processing software, which was written in Python. And what this estimates is social groups within a herd, as well as social levels, whether the cow is timid, somewhat social, or very social, as well as friendship rankings and scores for each cow. And it also allows the user to link pairs of cows and see the current distance between them. And these algorithms were, in general, based on density-based clustering algorithms as well as nearest neighbor algorithms.
So I was in charge of designing the actual case that everything kind of goes into for the anklet. So I went through about 5 prototypes, and as I progressed through them, we found out more of what we really want and how the size of everything is. So it kind of gradually grew larger, and then it shrank back to our current size. And I did all the microphone related work, so that includes getting the microphone to work on the anklet, as well as analyzing all the sound data that we received through the network. And I set up the whole MySQL database, as well as designed the structure on Amazon Web Services. And I set up the router that kind of takes the data from the Zigbee network, and it takes the data and figures out what kind of data it is and formats the data accordingly to be sent to AWS.
I was in charge of the activity profile for the cows. So I used an accelerometer to give me XYZ acceleration values for the cows below the hock leg, as well as an orientation of the accelerometer, which told me the orientation of the cow. I used this data I built a step tracker based on data from real cows. That was prototype 1. And then the activity profile was developed based on the orientation and the step count to say what percentage of the time the cow walks, stands, runs, and lies down. And I also do estrus or heat detection for the cows based on the activity of the cow. I also did router to database communication, where I used Amazon Web Services Internet of Things. We published it using MQTT, and then it was sent to AWS Lambda functions that run in the cloud, and then inserted into the MySQL database from there.
So I worked on the biometric sensors. At this point, just pulse collection and basically making sure the cow's healthy by monitoring its heart rate. If that falls too high or low, you've likely got an urgent issue that needs to be taken care of. I also worked on the hardware design, making sure that the PCBs were fully integrated and provided everything that's necessary to the chips and the peripherals. And the power budget, selection of batteries, making sure that we had the capability to keep the device operating for as long as it needed to be without causing the farmer to either waste a large amount of time on powering it or waste a lot of energy and that sort of thing.
So we didn't really have access to a cow at the last minute, and we took an alternative way.
So our customer was also Professor Kia, and he seemed very happy about the result. We installed the product in the lab because he doesn't own a farm. So we talked with him through how we implemented each step of our system and how the data flows through the system. And according to him, our project exceeded his expectations, and he could not be more pleased with the overall progress.
So for our concluding remarks, this project's been very rewarding. It's helped prepare us tremendously for the working world. It also exposed us to a life cycle of a full stack product. We implemented all the stages to the website from the hardware. We think our main strengths are extracting the meaningful insights from the data. We do a lot of analysis to provide the farmer with usable information. It has a lot of potential for additional features, and this code is going to be open source. Well, it's all going to be open source for researchers and other interested individuals who want to build off our work.
Yeah, we'd like to thank Professor Pisano, Professor Kia, Professor Arshak, and the TS helped us all along for completing the project. Thank you.
Without a final install, do you have any verification for the accuracy of the product?
So that depends, I guess, on the metrics that you're looking for. The pulse sensor was actually calibrated to detect in humans, and we'd have to recalibrate that for cows. The location sensors are probably going to be fairly accurate no matter where you're doing, because that's just based on the distance between the things. So we have reason to believe that the social profile is going to be easily transferable. Same for the accelerometer. We had a lot of practice making sure that making our movements as cow-like as possible for that.
Well, also, it was developed with a lot of samples of cows. So I have like 6 gigs of data I can pull up to prove it works with where it's been charted that the step tracker is detecting movement, as well as an accompanying video of the cow that was taken with each sample. So I can prove that it works that way.
Could you please explain how using the RSSI, it shows you the exact location of the animal?
Yeah, so how we envision the system is that in a mesh network, you can have data hopping from the cow's anklet devices to different router-like devices, which you can call location beacons. And these beacons are at known locations. So when they receive a message from an anklet device, they can measure the signal strength. And there's a roughly logarithmic relationship between distance and the RSSI value. So that's used to come up with the distance estimate. And then with 3 distance estimates, you can do trilateration.
What is the estimated cost for, I guess, per acre of land or per cow?
So each device at the moment is relatively expensive, but something coming out to something like $100. But the thing is, the vast majority of that is actually just manufacturing the PCBs. So the final product should have like more customized bulk manufacturing, which is obviously going to be much cheaper. As for the land estimates, each static node, really all you need is the main board, which costs something like, I believe, $50. And that covered no.
The chip itself is only like $3 really. So actually,
Well,
like the main.
Yeah, the main cost is still going to be the board and providing energy and all the peripherals to it. And the cost of that is going to be like something like I'd estimate around $50 for, I want to say, a 300-meter radius, right? And most farms are most of the farms that we're looking at. So a lot of our project focused on dairy cows, which tend to sit down for the vast majority of the time. So we have a very relatively confined area. So in all likelihood, you're not going to need more than, say, 10 of these beacons. So the total cost we'd estimate for a small farm with, say, like 20 animals would be somewhere around $1,500, which is comparable, if not better, than most competing technologies.
How do you know your anklet actually fits on a cow?
Oh, so we did a lot of extensive testing here. I went out to a slaughterhouse and measured or molded a cow leg. I was going to bring it in, but it had started to rot due to lack of preservatives at this point. We did a lot of extensive testing to not only make sure that leg would fit on the cow, but also that the cow wouldn't be able to shake it off and that it would sit comfortably and still allow for a collection of the biosensor data as well as the rest of the data.
I had also like tested one of the earlier prototypes on a cow, and like basically the main issue was the strap was too short, and like I had to pull it at the very end. So in general, this case size is pretty much the same. So I have reasonable, I guess, claim that it would fit well.
What's the risk of the product breaking?
Um,
Like if the cow lays down on it or kicks something?
Not very high. The case is very well designed.
I mean, currently it's just 3D printed because we're still prototyping the different ways to keep all the parts in there stable and not moving, and we want to keep working on it. But currently, I've been calling it kind of like a brick because it's really hard. But I think it's durable enough. As all I can really say. I haven't tested on a cow, like I said, so.
Does a cow farm, if I had a farm, does a farmer typically collect this kind of data? And if he doesn't, what are some of the things that he could do with it that would improve the economies of his farm?
So a lot of farmers do collect this kind of data. Not a lot of them collect all of this data. one of the key things that we kind of set out to do initially with this project was to make sure that the cows are as healthy as possible, which the wide range of metrics really does allow us to do. A lot of farmers are going to be like either collecting pulse or activity or doing heat detection, but our product does all of these things in one. This also lets us like correlate the different things for researchers and veterinarians to be able to say, oh, your cow is in heat, and also you've got, I don't know, a really high amount of noise in the environment. It's possible that the two things are correlated. For instance, greater mooing, which wasn't known before to correlate with estrus. Now we have that information. So we can also sell it to interested individuals who want to say make more products like this that are interested in kind of tackling the hardware aspect while we've got a really good handle on the software.
I have to ask the obligatory battery life question. How long does it last?
So the batteries that we selected, we did a worst case analysis. They're going to be lasting at least a year. Unfortunately, the batteries that we selected also have a 35 ampere max current, which is really not what we wanted. We wanted low current, high storage, and we kind of went the opposite direction accidentally. So the current design does have enough energy to last for a year, but in all likelihood it's just going to blow the chip out in the first second if we try to power it. So getting a better battery, the goal would be to last it for at least a year, hopefully longer. The device really only needs to last 10 years, which is the average lifespan of a cow.
So do you say that on first power on the chip's going to blow?
With the current batteries, if we were to power it, yes. The way that we've done it for now is just using most boards and kind of avoided attaching the batteries directly to it.
All right, thank you.